Welcome back. So we continue the discussion on the hinge spring model. So what we have discussed so far that the different components of hinge spring model, what you have different components, and then what the hinge and spring does, and different direction of the motions, and then we'll be primarily focusing on this flapwise motion. So this is discussion on hinge spin model. So we'll develop this simplified model. Idea here is that though this model is simplified, but this incorporates all the interacting effects so that we have a simplified system to now. So when we develop this, the development includes how the rotor responds to the following sources of loads. So it could be rotor rotation, gravity, steady yaw rate, steady wind, yaw error, linear wind shear. So essentially this whole development of this linearized model incorporates the effects, how the rotor responds to this set of loads, okay, including rotor rotation, gravity, steady yaw rate, steady wind, yaw error, linear wind shear. So all these are part of that. Now, these loads may be applied independently or combination with. So this can be applied independently or in combination. So what this analysis would provide a general solution for the rotor response, which is so solution which will be a function of blade azimuth, the angular position of blade rotation. Okay. So obviously the solution would contain different terms. One could be independent of azimuth position. Then it could be a function of sine of azimuthal position or the function of cosine of azimuthal position. So the solution will have three terms. One is that independent of azimuth position, function of sine of azimuthal position, function of cosine of azimuthal position. So this essentially would contain three different components. So the whole development is broken into two components. Number one, free motion. Number two, forced motion. Okay. So the free motion that includes the effects of gravity and rotation, and this includes steady wind and steady yaw. Now, anything we deviate from here, the steady wind or steady yaw. So any deviation will be considered as perturbation. So if it is a steady yaw or if it is a steady wind, it can be considered as a perturbation. So now the thing that is important. So these are the overall picture of the development of the hinge spin model. So one is that the rotor responds to different forces. So what we talk here is that to develop, to develop that simplified model, uh, we look at the rotor response to different forces. It includes rotor rotation, gravity, steady yaw rate, steady wind, yaw error, linear wind shear. And then these forces we will consider sometimes independently and their subsequent effect on the model development, or we take some of them in combination depending on the impact of those sources of the forces. Now the solution that finally eventually will evolve, that would be the function of blade azimuth and the angular position of the blade rotation. So we would consider some independent of the azimuth position, then function of sine or cosine, and then the solution would evolve accordingly. And while doing this particular development, so we'll consider two ways. One is the forced motion or free motion. The free motion includes the effect of gravity and rotation. Forced motion includes steady wind and steady yaw. And any deviation from those steady wind or steady yaw would be considered as an perturbation to the system. Okay. So this is the overall idea, what based on which we are going to develop this simplified. The important thing is that coordinate system. Okay. So one has to define the coordinate system. Because this should be important to derive all the model analysis, their the model development and their analysis, all the equation of motions. So what we can see is, let's say, particular wind turbine. Let's say if we say this is an turbine and we have all the blades. Okay, so what is important from this line to this is psi, maybe center. So that is so where we can apply that. So here, what is the? It's a three-bladed system. Okay, and so what are the factors that affect the motion? One, geometry. Two, rotational speed. Three, blade width. And any other external forces that would be considered as we keep on doing our analysis. Obviously, some assumptions are there. Okay. So what we can say that A, the blade has a uniform cross section. Okay. B, the blade is rigid. Okay. And the blade hinge may be offset from the axis of rotation. The blade hinge may be offset the axis of rotation. D, when rotating, the rotational speed is constant. So these are some of the assumptions that would be associated with this. What so any other hinge spring stiffness or offset for the model we would take into consideration while discussing this whole thing. Now, I mean, it's to so we'll kind of draw this axis system. So let's say okay. So here, so we'll have so that's the one, and this would be one there. This goes there. Okay, and all these we have this and this is something. Okay. Now we say this this is psi, this is beta. Okay, this is y double prime. This is double prime. This is my rotor axis. This is crosswind V naught. This is x prime, y prime. This is wind speed u, and this is q. That is essentially my yaw axis. Okay. This is wind. This is crosswind. This is rotor axis. So that's pretty much the axis system. So this is my coordinate system for hinge spring model. Okay. So here what we have x prime, y prime, z prime. These are coordinate system defined by the turbine itself. Okay. Whereas x, y, z fixed to earth, x price is okay. Z prime is prime is perpendicular to x prime in Z prime. Okay. Now we have x double prime, Z double prime. These are axes rotate with the rotor. So for this graph or configuration, shown here, x double prime is aligned with the blade, but in the plane of rotation. Size azimuth angle of the blade with respect to x prime. Okay. So blade itself is turned out of the plane of rotation by the flapping angle beta. So beta is the flapping angle. So essentially the blade itself is turned out of the plane of rotation by beta. So also this particular figure reflects the assumption that the direction of the rotation of the rotor. So the direction of the rotation of the rotor and yaw is consistent with right hand rule with respect to the positive sense of the x, y, z axis. So specifically when looking in the downward direction, the rotor rotates clockwise. Now we can see the other thing. Basically, let's say so this is x double prime, this is omega z double prime, this is r, this is beta, main shaft, which is free stream wind, then that is r into 1 minus e, that is e into r, so that is k of beta. So that's the top view of hinge spring model definitions. So that's what you will get to see. So this top view here, what it shows that mm, that a blade which has rotated past its highest point, that is azimuth of pi radians, and is now descending. So specifically, the view is looking down the y double prime axis. So that's what you'll have this. I mean, what you see here, that this is the picture that you have. So, I mean, we have this assumption to develop that. I mean, some of the assumptions like the blade has uniform cross section, blade is rigid, hinge may be offset from the axis of rotation. Um, then we have this coordinate system here, where x prime, I mean xyz is attached to the earth, x prime, y prime, and z prime or z prime. That's the coordinate system defined by the turbine itself. That means that coordinate system is sitting on the turbine. So one, you have x, y, z at the earth. Then we are setting one reference frame at the turbine that is designated here x prime, y prime, and z prime. Then if you see x prime is along the tower, that means if this is my turbine tower, then x prime is along the tower. Z prime is the axis of rotation. That means this is Z. So this is how it is rotating. And Y prime is perpendicular to that X prime and Z prime. Okay. And then you have X double prime here, Z double prime, Y double prime. These are the axes which rotate with the rotor. That means as rotor blades rotate, so this X double prime, Y double prime, and Z double prime also rotate. So here, as it's shown, essentially your so this should be x double prime. So x double prime actually aligned with the blade, but in the plane of rotation, and psi is the azimuth angle, beta is the flapping angle. Okay, and then we have this top view of this thing, where you can see. So this is looking down through the y double prime axis, and then you get to see how this blade is hinged, and with the radius of the rotor dia along with that. So this is what the coordinate system that we define to develop the model. So that we have all the information in place to carry out the development. Okay, we'll continue this discussion in the next session.